So today our objective is very slightly different from yesterday's objective. It's still Pythagorean Theorem. It's still using it, but this time we have to visualize it in a three-dimensional shape. So we're going to be drawing some three-dimensional shapes. So our objective is to understand and apply the Pythagorean Theorem to three-dimensional shapes and real-world applications, so AKA word problems. Now, if you noticed on the homework last night, some of them had pictures and a couple of them did not. And you needed to provide that picture in order to see where did the numbers go, where was the right angle, how did they line up as A, B, and C. And if you're not going to draw the pictures in geometry, you are in a big trouble because that's what you need to do to help visualize. So Pythagorean Theorem doesn't change now that we're talking about three dimensions. What changes is how do we find the triangle. So we're going to have to do some drawing. Now, most of the time, the shape that we're going to be using is some sort of box, okay? And because boxes are nice three-dimensional shapes. So let's just take a moment and let's practice how we draw a three-dimensional box on two-dimensional paper. It's actually kind of easy. So first thing I'm going to do is draw a rectangle. Everybody's drawing a rectangle. And you have two ways to do this because one way is going to require a little bit of erasing. The other way will not. So we're going to do it both ways. One with erasing and one without. Okay? So if you don't have an eraser, you're going to need one, or you can share one. I should have a couple in that little container. So what I'm going to do is draw now a second rectangle. Okay, everybody's got to watch. That second rectangle is going to overlap with the first one. How is it going to overlap? It's just going to be slightly higher and slightly to the right. It should be of the same size. So what's nice is you've got your line paper, and you can use your line paper to help you keep things kind of evenly spread out. And then what you're going to do is connect the vertices, and the vertices are the corners of the box. And then erasing is going to indicate something that's inside that the human eye couldn't see, but if I was Superman, I could see. So here's what Superman's going to be able to go through. I'm going to have to... So basically what I'm doing is this front rectangle that's solid black, that is the front of the box. Okay, so this is the front of the box. Those dashed lines are all the pieces that you can't see, all the pieces you can't see, okay? And they do it on an angle to give you a perspective so that you can actually see more of the surfaces of the shape, okay? So that is doing it with erasing. Now let's do one that doesn't require erasing. So you start with your rectangle. Okay. And this one, you just kind of draw three corners. So three sides. You're going to connect over on the right and in the back. And then this is where you got to put the dashes in. So here's your Superman vision. Okay. And what's interesting is you can make this kind of an optical illusion. If you focus in on the solid black, that's the front of your box. But if you change your focus and you look here, all of a sudden this will pop out in front. Okay, so you can kind of fool your eyes into seeing. kind of the shape pops a different direction.
So how many right
Okay.
angles?
Well, because it's a rectangular prism, every surface is a rectangle. So we have right angles everywhere you look. Okay. Now, what we're going to be dealing with is notions of, let's say I want to pack something into this box. And I want to figure out what's the biggest thing that I can pack. So looking at the box, can somebody describe the direction my object should rest in this box in order for me to get the maximum sized object in it? And I'll do this. Let's add some letters here so that you guys can use the letters to help you. A, B, C, D. Oops. E, F, G, H. Okay, so Giovanni, you've got an idea. Can you tell me some letters that would describe the longest part of this box?
H and G.
So H and G. And I'm going to say it's actually not the longest part of this box. Cameron?
E and F.
E and F, again, E and F and H and G are actually the same exact length. So they're still not the longest length in the box. Jonah?
A and C.
A and C would be the longest length. So here's what,
But then D and B would too.
uh-huh. So what we're going to be doing is figuring out that if you think back to the video we saw at the beginning, where he was talking about you measure television by the diagonal, because that's the longest part of a rectangle, it's diagonal. So in these three-dimensional shapes, this becomes the triangle that you're going to be solving for. So you're going to have a diagonal from A to C. You're going to have a diagonal across the bottom of a shape. And then you're going to have one of the actual sides of the box will be another side. And so here's your right angle. Okay? So not only do we have right angles on the faces, all 6 faces have 4 right angles, but you also have right angles on the diagonals. Okay? So that's what we're going to be using for our particular solving. All right? Does everybody have that idea? So I'm going to write underneath here segment AC and segment DB, segment FH, and let's see, which one am I missing? And segment EG. Those are all the diagonals of the box. They are the longest lengths in the box. In other words, I could draw 4 different triangles going diagonally in the box. Okay? Now, I'm going to share with you probably the toughest problem. So if you get this toughest problem, you use this as your role model, you guys should be doing great. They're going to be a little bit tricky on us, because if you notice, I've got 2 diagonals in that red triangle. I've got a diagonal at the bottom, that AF, and I've got a diagonal from the entire 3-dimensional box, that AC. So in order for me to figure out a missing length on that red triangle, I'm going to have to figure out 2 different diagonals.
Wait,
Okay?
what's the missing link?
That I'll reveal in just a moment. Okay, Joey?
Wait, so what about the space between A and B in the red line? Like, what is that?
That would be called the length of the box. BF would be called we can add those in there. This is called the length of the box. BF, that would be called the width of the box. So what we're looking is at one of the bases of the box. So a base is what lays flat on the ground. We have a length and the width. And then what do you think we call CF?
The height?
That's the height of the box. Remember, that's the 3rd dimension in a 3-dimensional shape. 2-dimensional shapes have lengths and widths, but only 3-dimensional shapes add on the height. Okay? So those are the three that we're going to be using. Those three numbers are going to help us solve any three-dimensional problem. All right, so let me give you the problem, and we're going to have to write this one out. So a box used for shipping narrow copper tubes or pipes measures 6 inches by 6 inches by 20 inches. What is the length of the longest tube that will fit in the box? Get it together. Given that the length of the tube must be a whole number of inches. So in other words, what they're telling us is that we are not going to, if we get an answer that's not exactly a whole number, we're going to have to round it to a whole number so that'll fit. Okay? They don't want to have any others. By the way, what do you use copper piping for?
Plumbing?
Plumbing.
Yeah.
Okay. So I'm going to recreate our box. Now, I'm looking at homework for tonight, and we have, looking at your turn, guided practice, and independent practice, and most of the problems show a picture. There may be a couple where you're going to have to come up with a picture. All right. So we're going to write the dimensions on this box. Oh, and I want to also figure out a couple of things. We're going to call him R. We're going to call him S. Okay. And these guys, we've got length. And of those three numbers, 6, 6, 20, which one do you think the length is? It's dimensions of a box. Don't deal with inside the box. They deal with outside the box. So which one? Nope. It would be 20. Okay. And then this side here would be called the width. And he would be 6 inches. And this side here is the height. And he's also 6. Okay. So we have inches. So we have 6 inches for this height. We have 6 inches for the width of the box. We have 20 inches as the length. And our job is to figure out, we want to know what R is. So what we're trying to solve for is R. In order for us to figure out R, we have to know S. Okay? So S, we'll color him differently. There's our right triangle. And we actually know the two legs. One leg is the length. What's the other leg that we know? That's the width of 6 inches, right? So to figure out S, we have the width of the box plus the length of the box squared equals the diagonal of that bottom part of the box. So we get 36 plus 400 equals s squared. I'm going to use symmetric property. Adding up 36 and 400, we get 436. And then we're going to go ahead and take the square root. Well, actually, I'm going to leave it like that right now. And the reason why I'm going to leave it like that is because when I figure out what r is, I need to know s squared. So I can leave it right now as s squared. Okay, let's go to r. So in r, what part of the triangle does r play? He would be the hypotenuse. So what I'm going to color in differently. There's that triangle. Okay? Isabel.
Up top, what is the height? Does it say
6. Yeah, if you go back to the problem, it said 6 inches by 6 inches by 20 inches. I'm just sorry, it's all kind of crunched in. But yeah, that's another 6er. Okay?
For the box thing, what is that a B? RS and what's the purple thing?
It's the right angle.
This is just showing you where the right angle is. So it's a right triangle. Jacob?
Wait, so we're solving it. So first you have to solve the one for the bottom one.
Yep.
And then the hypotenuse of the bottom one will be one side, and then the height will be the other side of the
Exactly.
next one. You solve that one.
Exactly.
And that's it.
Exactly. We have to do Pythagorean Theorem twice. So that diagonal of the bottom of the box becomes the leg of the new triangle that we're doing. Okay? So here we go. Let's do the r. So the r has the s squared, right? So I'm going to write that first. The other leg is the height. Remember, this is the height that's over there on the left, the red. And then that's going to equal r squared. So we already know what s squared is. We got 436. And the height is going to be 6. We're going to square that. And that equals r squared. So that gives me 436 plus 36 equals r squared. So when we add, 36 and 436, we get 472. And then we don't want to know what r squared is, we want to know what r is. So what are we going to do?
Square r squared and 172.
Take the square root. Not square, square root. Okay? Square root of r squared is r. And then we're going to take the square root of 472. Now we run into a little bit of a problem if we're not allowed to use a calculator. We don't know what that falls between because we kind of stopped off at 400, right? So 20 squared. So we know it's going to be over 20 squared. So we can do this one of two ways. We could try to factor out perfect square factors. Look for 4s, and 4 goes in because 4 goes into 72. Or we could say, okay, I know it's over 20, so I could do a little guess and check system. What's 21 squared? So I get 1, 2, 0, 2, 4. I get 441. All right, what's 22 squared? 4, 4, placeholder, 4, 4. I get 484. Bingo. Just in that, I come up with my two choices. Okay? So I have 441, 484. And now I have to take the square root of each of those. So one's 21 and the other is 22. Okay? So now this is when we employ our little strategy. We're going to start with 21. I'm going to move it over to the left. And I'm going to add to it a fraction. So I'm going to subtract 472 and 441. So my number and the smallest perfect square. And then I'm going to take the two perfect squares and subtract them. And I get a 43. And then the last thing I need to do is divide 31 by 43. And I only need to go 2 rounds. That's it. And then I'll know how to round it. So I'm going to do, let's see. Let's go ahead. I'm going to go ahead and erase this stuff over here, since we don't need it anymore. And we'll do the long division. So 31 divided by 43. And let's see, that's going to go in 31.87 times. And that's going to give me 2130. Bring in that's going to go in twice, which is 86. So what I have at this point is 21.72. I'm going to round to the nearest tenth. Can the 2 change the 7? No. So my grand answer would be approximately, so little tildes mean approximately, 71 or 21.7, and the label would be inches. Now, remember what the question said. We can't do decimal answers. We can only have whole number answers. So what would be the longest length tube to the nearest whole number that we would be able to have? Now think before you answer that one. Think carefully. Okay, Taylor?
You have to round the 7 to the 1.
Okay, so let me ask you, if the maximum size is 21.7, and you're telling me to go to 22, have I gone beyond the box?
Oh, 21.
Just a little bit. This is one of those cases where if you have X amount of kids who need to get on a school bus, and you want to figure out how many school buses, and there's only so many kids that can get on a bus, and you come up with the answer of 5.3 buses. Can we have 5.3 buses? No. So then you have to think, in that case, you would need more buses. And you'll just have one that doesn't have as many kids on it, or you just reduce the number of kids per bus. This situation is saying, this is your max number, is 21.7. I need a whole number that doesn't go beyond the max. Okay? So the final answer would be 21-inch tube you'd be able to have.